The Ottobock C-Brace orthotronic mobility system is a microprocessor-controlled knee-ankle-foot orthosis developed by Ottobock SE and Karmer KGaA in Germany. It was first released in 2016, updated in 2021, and is cleared by the FDA as a Class II medical device under 510K, K1FIMF2823. The device is powered by a 24-volt rechargeable lithium-ion battery and integrates a real-time microprocessor-regulated hydraulic unit with embedded sensors that measure knee angle, acceleration, and ground contact. It is indicated for individuals with incomplete spinal cord injury, post-polio syndrome, or multiple sclerosis. The microprocessor continuously analyzes gait data from inertial measurement units found throughout the device's multiple sensors. The microprocessor processes this data within milliseconds and adjusts hydraulic resistance accordingly. Feedback algorithms ensure phase transitions occur without delay, and calibration routines allow the device to be tuned to each user's gait parameters. The hydraulic control system replaces static locking joints with dynamic damping. A titanium alloy piston regulates resistance through each user's unique gait motions while working in sync with the microprocessor to modulate the torque. The damping force is calculated as the damping coefficient multiplied by the velocity of the piston movement. The coefficient represents the resistance of the hydraulic fluid, while velocity represents how fast the joint is moving. The knee-ankle-foot orthosis, CAFOs, relies primarily on the hydraulic dampening system, which uses silicone oil to regulate motion. The silicone oil itself is highly compatible with the titanium alloy piston, based on its high temperature range, stable viscosity, and stable thermal and oxidation properties, making it ideal for the CAFO's daily use patterns. The hydraulic unit works in synchronization with the microprocessor to modulate torque precisely during stance and swing, reducing impact shock. Thermal management is achieved through passive conduction and convection. As hydraulic fluid moves through the damping unit, kinetic energy is converted into heat. The metal frame conducts heat outward, while natural air convection removes it from the surface. Fluid circulation distributes heat evenly within the system. The heat transfer rate is determined by multiplying the convection heat transfer coefficient by the surface area and the temperature difference between the device surface and the surrounding air. The microprocessor monitors thermal conditions and adjusts resistance if thresholds are exceeded. The sensor system integrates inertial measurement units, IMUs, force sensors, and angle sensors that are embedded within the brace joints. These are micro-electromechanical systems, MMs components, which do not require direct skin contact. The sensors measure knee angle, angular velocity, ground contact, and load force. Data is sampled at update rates up to 100 Hz, providing a smooth and immediate response. This information is transmitted to the microprocessor in real time, forming the input layer of the closed-loop control system. The control system operates on a closed-loop proportional integral derivative (PID) algorithm. The control signal is generated by combining three terms. The proportional term corrects the current error, the integral term corrects the accumulated error over time, and the derivative term predicts and corrects based on the rate of change. Together, they make sure the knee follows the desired motion, ensuring real-time correction of gait deviations and maintaining stability across variable terrain. Biomechanical function can be described by the torque relationship, where the torque at the knee is equal to the limb's moment of inertia multiplied by its angular acceleration. In this device, hydraulic and microprocessor control replace muscle torque to regulate this relationship. In the C-Brace, torque normally generated by quadriceps and hamstring muscles is replaced by hydraulic and microprocessor-controlled torque. This allows stance phase flexion and swing phase extension to be regulated according to measured gait parameters. Energy and power flow are managed by the 24-volt lithium-ion battery, which supplies current to the controller and hydraulic actuator. Power is defined as torque multiplied by angular velocity. This describes how much mechanical energy is being transferred at the knee during motion. Hydraulic damping absorbs excess kinetic energy during stance, improving control of deceleration. Optimized energy flow increases device runtime, though battery capacity limits operation to 6 to 8 hours per charge. Engineering simulations identify performance constraints. Thermal analysis shows maximum temperature concentration near the hydraulic unit with values up to 42 degrees under continuous operation. Mechanical stress analysis indicates maximum stress at the knee joint with values up to 30 MPa under peak load. These results inform material selection and reinforcement strategies. The device is constructed with a modular design consisting of a thigh shell, knee unit, and lower strut. Components are connected via snap-fit joints and quick-connect ports for hydraulics and sensors. Disassembly follows the reverse sequence, allowing for part replacement or servicing. Routine inspection is recommended every 3 months with annual checks of hydraulic fluid, battery condition, and sensor calibration. Market differentiators compared to conventional CAFOs include adaptive control with real-time adjustments, closed-loop feedback for consistent phase transitions, integration of rehabilitation and daily mobility in a single device, user-specific calibration, and clinical validation with long-term outcome data. Conventional CAFOs lack adaptive resistance and cannot provide stance phase flexion. Limitations include a weight of approximately 2.5 kilograms per leg segment, a cost of approximately $70,000 USD, battery life limited to 6 to 8 hours per charge, calibration requirements that must be performed by certified orthotists, and lack of water resistance for full submersion.